The threat of global warming and the finite nature of our oil reserves mean we have to look for sustainable methods of generating energy, away from burning the carbon in oil and coal. The sun still offers the greatest potential for clean energy. Silicon-based photovoltaic panels have come along in leaps and bounds, but wafer-thin solar cells could soon play a major role. We could produce our own electricity, even our own fuel for our car, from the sun. That's the vision. Nanoscientists like Serdar Sarasifti are working on this. On the one hand, it's quite traditional fundamental research.
On the other hand, nanotechnology is a very basic and diverse opportunity for solving problems. We use nanotechnology to capture sunlight and turn it into electricity or artificial fuels. In this application, nanotechnology could become the savior of the future.
But what does nano really mean? The word nanos comes from Greek and means dwarf. It refers to the smallest particles of matter. Nano isn't a substance, it's a unit. A nanoparticle is as small as this light bulb is small compared to the size of the Earth. While the aircraft Solar Impulse 2 had to interrupt its flight around the world because of technical problems, the scientists at the Johannes Kepler University in Linz present the next generation of ultralight solar cells. Even batteries can now be stretched elastically. Research into lightweight solar technology started with spaceflight in the 60s, but the scientists in Linz have broken a record.
We have the lightest, thinnest and most flexible solar cells in the world.
And the team of scientists made the cover of the renowned magazine Nature Materials. But it all seems very simple. The whole thing looks like cling film.
This is the substrate for our solar cells, which are 2 to 3 micrometers thick. That's a bit thicker than this film. A micrometer is 1,000th of a millimeter, and that's 70 times thinner than a human hair. In principle, you could even scrunch it up.
Or you could let it fly, thanks to Nano Research.
Conventional solar cells are made of silicon. This is the raw material, a silicon wafer. You can see it's quite thin, but not very flexible. I can't bend it. If I were to try, the wafer would break.
The scientists spent a year working on the problem. Then they had the breakthrough. They developed a new kind of electrode layer. The solar cells became corrosion resistant in wind and weather when coated in chromium oxide. This airship shows that the discovery works, at least during trials. But how does a solar cell actually work? The core of the solar cell consists of 2 semiconductor layers, an N layer and a P layer. If the 2 layers are brought into contact, the electrons migrate from N to P, and that produces a potential difference. When sunlight strikes this layer, the energy is transformed into electric current. But how do these new, wafer-thin solar cells benefit us in our everyday lives? Through intelligent clothing, for example, for communication, or to measure our pulse. And if we're out and about and without a socket to plug into, we could charge our phones with this solar bag. But the scientists in Linz have set their sights even higher.
There's the option of making these solar cells semi-transparent and integrating them directly into windows.
Where and how are these colourful solar cells made?
We're in the lab where the solar cells are made. You start with a substrate. When you start out, that's often a piece of glass coated in a conductive electrode. We first clean the glass with different solvents. Then we dry it in nitrogen. And then we treat the surface with oxygen plasma. That's so we can apply the layers thinly and uniformly. This is the plasma oven. We make the oxygen plasma in here. It's a pre-treatment so that the inks, the semiconductor inks, distribute more evenly.
The scientists use different nanomaterials for their solar cells. For example, a conductive material with large molecules, a polymer. That's how the first layer is made. You can imagine it like a printing process, which works this way in large-scale industrial production too. In a vacuum chamber, the scientists vapor deposit tiny quantities of metal, and that's it. We have a functioning solar cell.
The vision is to have a photovoltaic panel on the roof that doesn't just produce electricity, but a fuel that you can tap into in the evening and use in your car. A petrol or an alcohol, an artificial fuel.
The idea of taking sunlight and turning it into fuel has come from photosynthesis.
Photosynthesis is solar energy plus carbon dioxide and water. Combining these three things in green plants produces chemical substances which we then eat. These things go into the food chain, or they're stored in the ground for a few million years, and then we have oil, which we burn today. All of this is the chemical transformation of solar energy.
But we're still a long way off this vision of producing our own petrol, although the nano world has long become part of our lifestyle. But what are nanoparticles exactly?
Nanoparticles just refer to us having a variety of substances of certain smallness. There's a lot of nanotechnology in our food, coatings on cakes, for example, and in our ketchup to give it the right consistency. We have nanoproducts in things like sun cream. That's the best known one.
But can we just inhale the nanoparticles? The nano world contains risks as well as opportunities. In this case, we're benefiting from water-repellent clothing thanks to nanotechnology. Scientists discover new things and want to publish their knowledge. But what if a discovery is dangerous?
I would say that if a very dangerous nanotechnology were in my hands today that could destroy humanity, I definitely wouldn't publish.
On we go with other exciting discoveries from the nano world. When Sumo Ijima from Japan experimented with an arc discharge between carbon electrodes, he was amazed. He saw these tiny shapes. The atoms displayed a honeycomb-like hexagonal structure. Each hexagon had 3 connections. Research into these little tubes has become a huge field. We're meeting physicist Paola Ayala. She was the first woman in the history of her home country, Ecuador, to complete a PhD in physics. The two of them are researching nanotubes.
We brought some chicken wire. The characteristic is that it's hexagonal, but it's also an interconnected structure, just like in a nanotube.
This flat structure is the basis for the properties that the nanotubes have. They're electronic, optic, and mechanical properties that are all based on this nice geometric structure.
The most important properties of nanotubes are that they are much more tear-resistant than steel. You can also get nanotubes in semiconducting and metallic versions. Semiconductors are used in computers, and the metallic properties can be compared to a copper wire, for example.
If nanotubes are mixed with conventional plastics, they become extremely durable, ultra-light and strong. Nanotubes can therefore be used in bridges, aircraft and hockey sticks, and in wind turbines. What looks like steel spaghetti in this animation are networks of a large number of nanotubes. Such nanoparticles aren't visible to the naked eye.
Imagine it this way. 1 billion nanotubes are bundled into a single hair.
For the aviation industry, nanotubes are interesting because they are conductive and act like catalysts in fuel cells. That saves weight and energy. Scientists are even working on a spacelift with nanotubes as the connective material in order to send labs and telescopes up into space. Scientists at the University of Vienna are researching nanotubes too. They exist in liquid form and solid forms. Oleg is currently making some nanotubes himself. He's mixing this powder with alcohol to do that. It's put in a container called a sagar, which is placed in this glass tube and heated to 600 degrees.
We can watch through this window how this saga glows and the nanotubes grow.
This process results in single or multi-walled specimens that vary greatly in thickness. But not all are as homogeneous and beautiful as in this animation. To understand the different nanotubes, the scientists test their behavior and measure the optical and chemical properties using elaborate procedures. Nanotubes resonate like the strings of an instrument. Oleg has brought a sample that he irradiates with lasers. He has to place the light in such a way that the tubes react to the beam.
Every color has a certain frequency. We can use these frequencies to stimulate the samples and look for resonance frequencies.
Oleg has found the point at which the tube starts resonating.
If I add nitrogen, then you can see the beam better. What you can do with nanotubes is exchange some atoms or attach them to the nanotubes. That alters the resonating properties of the nanotubes. We can analyze these changes really well with the spectrometer.
It's just like tuning a ukulele. The light has to be tuned very finely to stimulate the correct tube. Philip demonstrates with 2 tuning forks.
We have a tuning fork. It stands for the nanotubes. And this tuning fork stands for the variable laser. If I try to stimulate the nanotubes, nothing happens with this nanotube because it's the wrong frequency. But when I find the right frequency with a second tuning fork, then I can see that the nanotube is resonating.
This room with measuring instruments that look like UFOs is a photon emission laboratory. The scientists are interested in the tube's chemical properties. Oleg is sending nanotubes into a vacuum chamber while X-rays knock electrons out of the sample. The tubes have to be extremely clean for this analysis. Paola Ayala has developed a cleaning method that's unique in the world. Only well-researched tubes can improve products like these phones.
The only candidates for overcoming the silicon age are nanotubes.
Smartphones contain as much computing power as a large computer once used to contain. Industry and science are still searching for even more efficient technologies.
When we think of batteries, for example, 90% of our mobile phones already contain nanotubes. They're used as connective material.
Nano visionaries around the world are researching how the tubes can compete with chip technology. A different idea is to use nanotubes as a means of transport for medication.
A nanotube has two surfaces that are useful, the outer and the inner surface. You can add molecules or objects that can be transported inside, or large molecules could drape themselves over the outside of the nanotube. That way, medications could be transported more easily.
But how do the carbon nanotubes get on with our bodies, our cells? And how well researched are the opportunities and risks of nanotubes? Work is underway to check if the tubes could harm the human body. We're meeting biochemist Eleonora Fröhlich from the Center of Medical Research in Graz. We want to know what happens when nanotubes are inhaled, the dangers in the detail.
Short, thick nanotubes are harmless, whereas the relatively long, thin, single-walled ones are the most dangerous. The reason we say they're dangerous is because of the similarity to asbestos. These long, fiber-like structures are dangerous because the phagocytes can't do anything with them because they're too long. The theories that currently claim that nanotubes are dangerous are unfair because the cleaning processes for nanotubes have only been discovered in the past 7 years at best. We scientists have nanotubes now, but still only in small quantities. And we've not yet been able to test the toxicology of these tubes.
But experiments have shown that inhaled nanotubes can enter the brain through the olfactory nerve or cause oxidative stress in our lungs and lead to inflammation.
We're in one of our labs. What interests us is how well our cells can cope with nanoparticles. The cells that interest us most of all are the cells in our lungs. That's one of the most delicate parts of our body. We're trying to recreate our lungs by cultivating the cells on membranes, where they live as they would in our bodies.
The scientist wants to find out how the cells in our lungs would react to the short nanotubes. But first she measures whether the cellular model is ready for the test. You can see that the cells change as a result of their contact with the carbon nanotubes, but not so that they die. If that were the case, you'd see that there were fewer and fewer cells. Of those we tested, which were 2 micrometers in length, there was almost no toxicity. They're much more harmless. That's compatible with the idea of using them in medicine. The short or even ultra-short carbon nanotubes are not comparable to the long carbon nanotubes. Maybe because they can be absorbed well by the cells. Phagocytes can cope with them, so they don't trigger chronic inflammation. Nanotubes have amazing physical properties, but their use in medicine is still a long way off.
A dream would be to have a nanotube that is filled with a cytotoxic cancer-fighting drug that carries something on its surface that is like a target substance,
krebsbekämpfenden Medikament,
so that it's absorbed more by cancer cells.
Substanzen sind, also vermehrt von der Tumorzelle aufgenommen wird.
It would be even better if all this contained a dye with which we could track how the tumor changes as a result of the treatment.
Nano seems to be the way to a medical revolution, but uncertain risks mean we still have to do decades of research, because behind these dwarfs there are still giant question marks we need to address.